Hello everyone, my name is Yuta Suzuki, and I am a student at Kanazawa University. I'm going to make a presentation entitled An Image Classification Model that learns MNIST image features and numerical information. My presentation consists of 6 parts. First, introduction. Second, related works. Third, proposed method. Fourth, experiment and result. After that, conclusion. Finally, future work. First, I'd like to start by talking about introduction. Here, I talk about introduction. In recent years, the development of deep learning technology has been remarkable. In line with this, deep learning has been applied to various tasks. For example, image recognition, voice recognition, and natural language processing. Among them, this study deals with the task of image recognition. In image recognition, we have often used convolutional neural networks. Convolutional neural networks is one of the DNN. Here, I talk about DNN. DNN is an abbreviation for Deep Neural Network. Deep Neural Network is a model of a neural network with many layers of neural net. In fieldwork, DNN calculating loss. And in fieldwork, DNN training with backpropagation to minimize calculated loss. Here, I talk about CNN. CNN is abbreviation for convolutional neural network. CNN is one of the DNN with convolutional layer and pooling layer. Commonly, CNN used for image recognition tasks. Just like DNN, in fieldwork, CNN calculating loss, and in fieldwork, CNN training with backpropagation to minimize calculated loss. Here, I talk about MNIST. MNIST is a typical image recognition task for handwriting numbers. The handwriting numbers range from 0 to 9, like this. And MNIST has 60,000 pieces of training data and 10,000 pieces of test data. In total, 70,000 images. When an image like MNIST is entered into the CNN, the image is vectorized in pixel values. CNN calculates loss in fieldwork, and CNN trains with backpropagation to minimize calculated loss in fieldwork. So, CNN trains no meta information such as concepts. Using MNIST as an example, CNN trains image features but not numerical information. Here, I talk about problems and objectives of this study. First, problems. When trained in MNIST, CNN does not train the numerical values and other meta information of the image. So we propose the models which train not only image features but also image meta information. Second, I'd like to start by talking about related works. Here, I talk about efficient net. In convolutional neural networks, it is a common practice to scale up the size of a model in order to increase its accuracy. However, there are many different ways to scale up, and there are hyperparameters. EfficientNet announced in 2019 scale up the model's depth, breadth, and resolution in a balanced way. EfficientNet is known as the most powerful image recognition model currently available. However, this model basically learns only from the features of the image. They can't learn the meta-information that the image has. Third, I'd like to start by talking about proposed method. Here, I talk about idea for proposed method. If you try to get model to train MNIST numerical information, penalties should be given based on the magnitude of the numerical error that the image points to. For example, if the model makes a misjudgment between 0 and 9, they are similar in terms of image feature, but the numerical implications are very different. In this case, big penalties should be given. And for example, if the model mistakes misjudgment between 3 and 4, they are not similar in terms of image features, but the difference in numerical implicance is not significant. In this case, small penalty should be given. Here we talk about what you can expect from the proposed method. For example, when given a table containing handwriting numbers like this as input, the model outputs like this. Comparing these two outputs, in the above table, the output is correct 5 in 6, but the numerical error is 9. In the table below, the output is correct only 4 in 6, but the numerical error is 2. In this case, the proposed model can be expected to produce the output as shown in the table below. Here, I talk about proposed method. The proposed method is that adding the term to give a numerical penalty to the loss function. Like this. This part is a term giving a numerical penalty. So, by calculating and training these laws, the model can train to reduce numerical errors. Here, I'll talk about proposed algorithm for calculating the numerical difference penalty. Like this, algorithm 1 was proposed as a method to calculate the numerical loss. Algorithm 1 requires a one hot vectorized correct answer label, true, and a predict result, predict, and numerical information for each label as a numeric. In addition, we also provide alpha as a hyperparameter to control the effect of the loss. The explanation of algorithm 1 is as follows. The first line calculates the numerical size of the correct label and stores them into numeric. The second line calculates the numerical size of the prediction result and stores it in predict numeric. The third line calculates the numerical loss between the correct label and prediction results by calculating the difference between true numeric and predict numeric, and it is stored in numeric loss. In the fourth line, numeric loss is multiplied by alpha and stored in loss to control the loss to a value that is easy to run. The fifth line return loss as the loss to be learned. Fourth, I'd like to start by talking about experiments and results. Here, I'll talk about the dataset used in the experiment. In the experiment, we use MNIST. MNIST is a typical image recognition task for handwriting numbers, like this. MNIST has 60,000 pages of training data and 10,000 pages of test data. In total, 70,000 images. Here, I'll talk about the model used in the experiment. The convolutional neural network used in the experiment was efficient at P0. For the proposed model, we adopt the loss, which is the combination of the categorical cross entropy and the numerical loss calculated by algorithm 1 as the loss function. And original model was adopted the categorical cross entropy as a loss function. Here, I'll talk about the evaluation in this study. The following three indicators are used to compare and evaluate the original and proposed model. First, accuracy. Second, numerical error per one image. Finally, numerical error per one image in the case of misidentification. Here, I'll talk about the result of accuracy. In comparing the original model with the proposed model, we use the maximum, minimum, and average of the 5 experiments. The comparison in accuracy is as shown in Table 1. It can be seen from Table 1 that the proposed model has higher accuracy in minimum and average. This confirms the high robustness of the proposed model. This is likely because the proposed model learns numerical information in addition to image feature. Here, I'll talk about the result of numerical error per one image. The average numerical error per one image was compared in Table 2. From Table 2, at maximum and average, it can be seen that the average numerical error is smaller in the proposed model. This result also confirms the high robustness of the proposed model. Here, I'll talk about the result of numerical error per one image in the case of misidentification. Table 3 compares the average numerical error per one image in the misidentification. From Table 3, at maximum and average, it can be seen that the average numerical error in the case of misidentification is smaller in the proposed method. Here, this figure shows the appearance rate of numerical errors in the case of misidentification. The horizontal axis in figure is the numerical error, and the vertical axis is the appearance rate of the numerical error in the case of misidentification. Figure shows that the proposed model has a higher appearance rate of small numerical errors, such as 1 and 2, while the appearance rate of large numerical errors, such as 5, 6, and 7, is relatively small. These results show that the proposed model has a smaller numerical error in the case of misidentification. Fifth, I'd like to start by talking about conclusion. Here, I'll talk about conclusion. In this study, we proposed a model for learning not only image features but also numerical information of image in MNIST. As a result, the proposed model has a high robustness and small numerical error. However, in the proposed model, numerical information was learned in addition to image features, but it is not suitable for learning other meta-information. Finally, I'd like to start by talking about future work. Here, I'll talk about future work. In this study, the model was trained numerical information in MNIST. Even in the object classification task like Cipher 10, we also learn meta-information by penalizing it as false. For example, if the model makes a misjudgment between a cat and automobile, they are very different. Big penalties should be given. And for example, if the model makes a misjudgment between a cat and deer, they are animal and animal. So different but close. So small penalty should be given. That concludes the presentation. Thank you very much for your attention.